Coming up shortly, we'd like to do some applications to physics, and we don't want to assume any previous knowledge of physics. So first I'd like to go through just some basics. We really don't need to know a lot of physics, but just some basic terminology and units so that you understand what we're talking about when we do some of these applications. So first of all, we saw a lot of motion in Calc 1 when we were doing derivatives, so let's review that real quick. First, we would talk about the position of an object. And usually we were just moving laterally, so position would be x, or vertically, so position would be y. But in general, you'll be looking at motion in your subsequent courses in general 3D space, and we'll just call that r for position. Typically this will be a vector. We're not going to get into vectors, but in three-dimensional space you'd typically represent that as a vector. And then we had, for our units, in metric, the standard unit is a meter, and in the imperial system, a foot. And then we saw velocity, v, which is the time rate of change of position. So the rate at which you're moving is your velocity. So this involves change in r with change in time. So meters is the r, and seconds is the time. And in the imperial, it's feet per second. Then you can talk about the rate at which the velocity is changing. That's our acceleration. And that is the time rate of change of velocity, so the derivative of velocity with respect to time. So velocity is meters per second. And then the units of time are seconds, so that's meters per second, or more compactly, we just say meters per second squared. It's not that there's a thing that's a square second, it's just that that's meters per second. And then likewise, feet per second, or feet per second squared would be our acceleration in the imperial system. Okay, so we've seen some of this stuff before. Something new, we're going to be looking at forces in the stuff we're about to do. So we need to talk about Newton's second law. Which says F equals ma, where F is force, m is mass, and a is acceleration. So Newton's second law relates the mass and acceleration of an object to force. Typically, that force and that acceleration, again, are vectors. But in one variable calculus, we're not going to be looking at vectors. So typically, we will be moving just in one dimension, either straight up and down or straight left and right, in which case we can avoid all the mechanics of vectors here. But this relates force to acceleration. So that F stands for force. M is the mass. And A is acceleration. One of the things we often do in physics is look at the forces on an object by adding up all those forces. Because the forces relate to acceleration, you can find the acceleration of an object by summing up all the forces. Really, this F here is the net force. If you add up all the forces on an object, divide by the mass, you'll have the acceleration of that object. All right. So one of the forces we're going to be interested in is weight. So weight is a very specific force. The weight of an object is a measure of the force of gravity on that object. So using Newton's second law, I'll just put a subscript W on there. So the particular force we're looking at here is weight. The weight of an object is its mass times the acceleration just due to gravity. So we're looking at just a single force, the force from gravity. Gravity will accelerate you downward towards the center of the Earth until something gets in your way. So we have a special symbol for that particular acceleration, little g. And depending on which system we use, so acceleration is meters per second squared or feet per second squared. Depending on the system, g can be measured experimentally to be seen to be 9.8 meters per second squared or 32 feet per second squared. Now, what are our units of force? So we know that force is a mass times an acceleration. And we already know our acceleration units for both metric and imperial. So what are our standard units of mass, first of all? We'll typically measure mass. In the metric system, it'll be a kilogram or kg. And in the imperial system, it'll be a pound of mass. And this can be a little bit confusing because we also have a pound of force in the imperial system, and I'll clarify that in just a second. So force being mass times acceleration, in metric, then it's kilograms meters per second squared. And 1 kilogram meter per second squared equals what we call a Newton in metric. So the standard force unit is a Newton, but that Newton is composed of kilograms meters per second squared. And then over in the imperial system, so you'd have a pound of mass times feet per second squared. And that is what we call a pound of force. So we have these two measurements that have the same name. Typically that little dash m or dash f is not written, only if there's some confusion as to which you're talking about that you'll put that in there. But let's think about why we have the same name for mass as we do for force. If we think about what is mass? Mass is a measurement of how much stuff there is in an object. If that object's here on Earth, or on the moon, or in orbit, or on Mars, the mass is always the same. It's just how much material is there. Now, when you take that mass and apply some gravitational force to it, you get a weight. A gravitational acceleration, you'll get a force, which is weight. And that weight will change, because this g that I've written here, that's g when you're on Earth. That g is different if you're on the moon or in orbit or on Mars or whatever. So your weight from place to place could change depending on the force of gravity, but your mass does not. But if you think about it, if you're just concerned with terrestrial life, as many people were several hundred years ago, the distinction between these two things is very minimal, because a pound, something that weighs a pound will always weigh a pound, because we're not sending stuff into space at that point. So there was really no need to really distinguish these units of mass and force. But now we really should have separate units. I mean, you even see in your everyday life things measured in kilograms, maybe your bag of Doritos or whatever. And that's really not a mass that we're talking about. We're talking force if we're talking about weight. But it has some mass, and they're just giving it in mass units because we're not concerned with how much those Doritos weigh on other planets. So we just give it in mass units. So you see some confusion just in everyday life between these units, but technically these mass units are for the amount of stuff. How much it weighs, that could vary depending on the gravitational force. And so we will be looking at, coming up, a calculation of change in energy. And change in energy is going to be based on applying a force. So we'll be seeing these force units, and we're not going to be dealing much with masses. The acceleration of gravity will typically already be figured in. We'll be given stuff in terms of forces, so I won't be writing that dash F. When we're talking about something and we're talking about the weight and we say pounds, it's understood that that's pounds of force. So next we'll look at calculating change in energy, but first we'll talk a little bit about what energy is and the various forms of energy.